So, this lecture is on how the greenhouse effect impacts weather. Most of us rarely think about the atmosphere, even though we may be mindful of our surrounding environments, like when we admire a beautiful tree. We often ignore that we are looking through the atmosphere, as it is, of course, entirely invisible. Although we can feel it, as when we delight in a soft breeze, we rarely think about the fact that what we are really feeling is the atmosphere. Nonetheless, the atmosphere is profoundly important for all life on Earth. Without it, Earth would be, obviously, a dead planet, in, as we shall see, more ways than one. To understand the impact that CO2 and other greenhouse gases like methane have on our climate, that's our global climate, we need to consider how the Earth's atmosphere reacts to solar radiation. Even though our atmosphere is incredibly thin, a single layer of lacquer on a basketball would be proportionally actually much thicker. It nonetheless keeps our planet from getting too hot and, somewhat paradoxically, from being too cold. Without our atmosphere, during the day, when the sun is shining on our part of the Earth, it would quickly get hotter than any temperature ever recorded on Earth, up to 260 degrees Fahrenheit. Alternately, at night, when the Earth rotates so that we are moved away from the sun and hence into darkness, it would quickly become far too cold, colder than any temperature ever recorded on Earth, as low as 280 degrees Fahrenheit, below zero. So how do we know this? These temperature extremes are exactly what happens on the moon, which has no atmosphere. Consequently, even if we didn't need the atmosphere to supply us with air to breathe, for example, if we were, say, wearing spacesuits, the Earth would still be uninhabitable because there would be no atmosphere to trap just the right amount of heat, solar radiation, to make our days neither too hot nor too cold. The simplest way to imagine the atmosphere in this regard is to think of it like a blanket over the planet. As with the blanket on your bed, the goal is to get one that is just right so that you'll be neither too hot nor too cold. What you're looking for is a blanket that Goldilocks would love, one that is just right. Incidentally, some scientists argue that the blanket analogy is a better way of imagining the greenhouse than imagining it as a greenhouse effect. And the book we read, Bending the Curve, actually has a chapter on this. Hence, if they had their way, we would not be talking about the greenhouse effect, but rather the blanket effect. Although the analogy of a blanket is useful, it nonetheless quickly breaks down. For example, our atmosphere not only keeps heat in like a blanket, it also reflects some, and that's about 29% of solar radiation back into space. Blankets do not, both keep heat in and keep it out at the same time. Nonetheless, this is an especially important service that the atmosphere performs, as some of the radiation reflected back is deadly to life on Earth. Thus, the atmosphere makes life possible in three major ways. First, we need it to breathe. It keeps the Earth's surface temperature just right for life. And three, it shields life on Earth from particular forms of solar radiation that are deadly. Consequently, maybe we should all think about the atmosphere a little more than we do. Incidentally, practitioners of meditation do just that, as the primary focus is always on the life-giving atmosphere, the breath, from when it enters the body to when it leaves. So what is the role of these so-called greenhouse gases in the atmosphere? So 99.9% of the Earth's atmosphere is composed of nitrogen, oxygen, and argon. As these molecules don't have an electric charge, they do not trap incoming solar radiation. If the Earth's atmosphere did not have trace elements of other gases, such as CO2 and methane, it wouldn't be able to hold the sun's heat in like a blanket. Hence, we call these gases greenhouse gases, as they are responsible for the greenhouse, or could call it the blanket effect on Earth. Specifically, once solar radiation strikes the Earth or oceans or ice, it bounces back towards space. This is especially happens with light-colored surfaces like sheets of ice near the poles, which work as sort of like mirrors. This is also why, wearing light or white-colored clothing in the summer is far cooler than wearing black. As 99.9% of the gases in the atmosphere, and that's nitrogen, oxygen, and argon, would let this energy go right back into space, the Earth would quickly heat up so that the oceans would begin to boil during the day. Alternately, at night, it would get so cold that even CO2 would turn to ice, to dry ice. However, when this ongoing solar radiation hits a molecule of a greenhouse gas, which are electrically charged and vibrating, it trips back into space as blocked, and it bounces off these molecules. Even though these greenhouse gas molecules only exist in trace amounts in the atmosphere, there are enough of them so that the outgoing solar radiation then begins to bounce around between these molecules instead of going directly out into space. Hence, thanks to greenhouse gases, our atmosphere is warmed by this solar radiation bouncing back and forth between these molecules. However, because there are not too many of these greenhouse gas molecules in the atmosphere, they do not trap so much heat that they make the planet uninhabitable for human beings and, other life on Earth. This is, incidentally, exactly what happens on the planet Venus, where there are so many greenhouse gases that the average temperature is between 800 and 900 degrees Fahrenheit. Most of these greenhouse gases are, in one way or another, naturally occurring on Earth. For example, the gas that traps more heat than any other is water vapor, such as in the form of clouds. Next in line is CO2, which also has natural sources, such as deep ocean vents, usually caused by volcanic activity, and when plants and animal material decays, which incidentally also releases methane. Other greenhouse gases like ozone and nitrous oxide can also be naturally occurring. These naturally occurring greenhouse gases are a good thing because without them, the Earth would be like the moon, wildly swinging from being either too cold or too hot to support life. The difficulty is that these gases need to be in a delicate balance in the atmosphere. If, for example, there was not a sufficient number of these greenhouse gas molecules floating around, the Earth would not be able to retain enough incoming solar radiation to make the Earth habitable. Alternately, and this would be the same as with Venus, if there are too many of these gases, then the Earth would heat up so much that it would be largely uninhabitable for most life that now lives on Earth. One could, sort of imagine a lab experiment in which we played with the percentages of these greenhouse gases. As we added more, the temperature would go up and down as we subtracted some. Unfortunately, this is not a hypothetical experiment, but rather one that human beings have been inadvertently conducting on Earth for the past few hundred years, especially the last 60 or 85 years, during which our species has been releasing vast amounts of greenhouse gases into the atmosphere, principally CO2 and methane. While it may seem surprising that human beings were able to emit a sufficient number of greenhouse gases to make changes to the global climate, recall that 99.9% of the atmosphere is not composed of these gases. Hence, adding just a few parts per million of CO2 can make a difference. Adding 100 parts per million, which was what we did in the last 60 years, has made a profound difference to our climate. Not surprisingly, all these greenhouse gases are heating up the planet. We call this global warming. Incidentally, even though the sun is heating our planet via greenhouse gases, this solar energy is nonetheless essential to our future as we leave fossil fuels behind. And that's because solar energy is either directly or indirectly the source of 4 out of the 5 of the principal forms of renewable energy: solar, wind, hydroelectric, and biomass. Photovoltaic solar cells transform energy directly into electricity. They do so as these extraordinary little solid-state devices convert photons hitting their surface into electrons, which is, electricity. Solar energy can also be used to heat water into steam in order to turn generators that produce electricity, or heat it to temperatures to provide domestic hot water. Solar energy can also directly heat properly designed buildings. The sun's energy also indirectly causes wind by way of differences in atmospheric, and by that I mean barometric pressure. In other words, because the sun does not uniformly heat the Earth's surface, owing largely to cloud cover and the way that different landscapes absorbed heat, air moves from source to sink, from hotter, high-temperature areas to cooler, low-pressure ones. We call this atmospheric movement wind. Wind turbines use the moving air to turn generators that produce electricity. When the sun's heat hits the earth or oceans, it can also release water into the atmosphere through evaporation. Similarly, during the process of photosynthesis, plants add water to the air through transpiration. When this water returns to the atmosphere, it returns to the surface as rain and is not directly absorbed by the earth, this runoff forms streams and rivers, which can be used to turn generators to produce electricity, usually after the water is dammed up in order to make sure that it's constantly available. While there are other forms of renewable energy, like geothermal, which uses the Earth's own, sort of resident heat, and tidal, which uses the moon's force as it's pulled on the Earth, specifically our oceans, to produce electricity or heat, the lion's share of renewable energy in our future will either directly or indirectly come from solar energy. In any event, CO2, methane, and other gases are called greenhouse gases because they all contribute to the greenhouse effect. As we have seen, greenhouse gases, and we usually call those GHGs, are not in themselves bad. Without them, Earth would be too cold to be habitable. However, because we have been pumping greenhouse gases into the atmosphere for the past 400 years, especially the last 60 or 85 years, our planet is quickly warming. We initially referred to the impact that these increased levels of greenhouse gases have on the planet as, not surprisingly, the greenhouse effect. But that name was supplanted by global warming, as it underscored the fact that the greenhouse effect was heating our planet. However, when we realized that an increase in atmospheric gases like CO2 and methane, is changing our global climate in a range of ways, such as with more severe weather events like hurricanes and monsoons, more severe droughts, changes in regional weather patterns, and all that, which we're going to take up in detail in the next segment, we began to referring to all this and global warming as climate change. But this is more than just a name change. This marked a significant change in conceptualizing the problem. When we thought in terms of global warming, we often just imagined a single cause and effect, and that would be, melting polar ice, which would result in global sea level rise. Consequently, while this alarmed, or at least should have alarmed, people who live near oceans, for many inland people, this did not seem like a cause for much concern. Moreover, as this ice was taking quite a while to melt, it meant that the oceans were only slowly beginning to rise. Between 1900 and 1990, they only rose at the rate of 1.2 to 1.7 millimeters per year, which is it's about 1/20th of an inch per year. Even though this rate increased to 3.4 millimeters, and that's about 1/12th of an inch per year by 2016, it still seems slow. However, sea level rise, when coupled with low atmospheric pressure, and very powerful winds can drive ocean water inland, which is what happens during a hurricane or typhoon. This, quote, storm surge can be extraordinary. When it happens during high tide, this tidal surge can be almost incomprehensible. At one point during Superstorm Sandy, tidal surge was 19 feet. During Hurricane Karina, tidal surge was 34 feet. So imagine a wall of water taller than a 3-story building coming from the ocean and moving down your street. Not surprisingly, whole houses and their occupants have been swept away during such tidal surges. People used to ask me pretty regularly, when is global warming or climate change going to happen? So the fact is, this is just a misguided question. It has already begun. Since 1880, average global temperatures have increased around 2 degrees Fahrenheit. Indeed, it has not only already begun, it's already at a crisis level. However, we have recently given it, hence, by the way, we've recently given it another name, which is not climate change, but the climate crisis. In order to underscore that the problem is at crisis level, the climate activist Greta Thunberg expressed the severity of the immediacy and problem in just 5 words, and that is, quote, "Our house is on fire." Imagine someone running through your house screaming, "Our house is on fire, our house is on fire." You would no doubt immediately become alarmed and do something, which is exactly what Thunberg wants you to feel and do about the climate crisis. In order to understand the immediacy of our climate problem, we need to consider how it is impacting more than just sea level rise through weather events like tidal surges. So these are going to be the subject of our next segment.